Saxon's Trig, Lesson 21, on page 150, is about evaluating functions, domain and range, types of functions, and test for functions. I failed to mention in the earlier video when we did our trig words of sine, cosine, and tangent that those are called trig ratios because they form fractions, but they're also called trigonometric functions. So in this lesson, they want to explore more the term function. So a function is where I plug in a number and I get a value answer coming out of that. And when this works, I have two other terms, independent variable and dependent variable. So if I have x squared plus 2, and I am picturing plugging in the number 1, I'm choosing to plug in a 1. That makes this x the independent variable. And then if this all equals y, y's answer depends on whatever I'm choosing for x. So x is the independent variable, y is the dependent variable because it depends on what I plug in for x. I get a very different answer if I plug in 1 squared plus 2 is 3, or if I plug in 2 squared is 4 plus 2 is 6. Different answer for those. Now, when we switch from equations to a different format, instead of the equaling y, it equals f of x. This is getting into the function terminology. So the f of x is doubling as my dependent variable, and it can still equal whatever the equation will be. But you're going to see a format, f of x, h of x, h of theta, and it's typically in this parenthesis with whatever your independent variable is listing here, but the overall combination with another letter, f, h, those are typically the ones that you'll see the most often, but we might encounter another one here within the book. So these are now in the function format. So let's talk a little bit more about that. If I am dealing with a function, then I can picture it as if it was a machine. So what's coming in are my x values. What's coming out are my x of x values. And what is in the machine is the equation that we're dealing with. What they will ask you to do is to solve for a provided x answer. So if you look at example 1, it says, given the equation f of x equals x squared plus x minus 10, find f of 5. They want you to plug in a 5 where the x is not only here, but in the equation as well. So when you solve for f of 5, you're going to substitute in 5 squared plus 5 minus 10. So the rest of the problem stays the same, but the 5 goes in everywhere there was an x, and then we merely solve that. So 5 squared is 25 plus 5 minus 10. 30 minus 10 is 20. So the answer when I plug in 5 is 20. And that's what I would actually box, that f of 5 equals 20. Now example 2 provides f of x equals x squared plus 1 as the equation. And it says find f of x plus 2. So everywhere there is an x in this, I will plug in an x plus 2 instead. This one is a parenthesis squared. The x plus 2 gets filled in and the plus 1 is still there. So when I go to solve, I immediately see that this is squared, therefore it's written twice, or I do the FOIL, or I do my shortcut. Just rewriting for my answer. X times x is x squared. X times 2 is 2x, doubled for the middle term to 4x, and 2 times 2 is 4 plus 1. I have only one like term. X squared remains the same, 4x remains the same, but 4 and 1 don't have x's, they're like terms, they go together. and that becomes the answer for plugging in x plus 2. Example 3. This one is given in h of theta. The equation is sine of theta, and they want me to solve for root 3 h of 30 degrees. So everywhere we have a theta, we're going to put a 30 degrees. So this is the actual equation that I'm doing, so I'm going to keep this 4 root 3 with the answer that I'm working on. And then h of theta is actually sine of 30 degrees. And this is what I need to solve. So I need my reference triangle of 30, 60, 90. Remember that the hypotenuse is 2. Opposite the 30 is the smaller number 1. Opposite the 60 is the root 3, the larger 3, although the concept root 3 is smaller. So once I'm here and I'm working with the 30, I know I want sine. Sine is opposite over hypotenuse because it comes from so. Make sure you can still see that. And the opposite of 30 is 1. The hypotenuse is 2. So we have 4 root 3 multiplying with 1/2. So this implies over a 1 to make it a fraction. The 2 and the 4 will reduce down so that we get 2 root 3, no change there, all ones in the bottom. So that's as far as that goes. 2 root 3 is the answer we're looking for. Now, part B changes gears just a bit and talks about domain and range. Now, domain are the list of numbers that I can use to plug into the equation that makes it work. The range is the list of answers that can possibly split out of whatever the equation was. So their definition for a function in the box, which any box is important, is a function is a mapping or a correspondence between one set called the domain, the things I'm putting in, and the second set called the range, such that for every member of the domain, so every x I can plug in, there will be an answer and exactly one member in the range. So every x has to have a y. You can't put in one x and get 2 different answers. You can't put in an x and not receive an answer. If these things are happening, I don't have a function. So example 4, they give us f of x equals root 10 minus x. And it says to find the domain of f. Now, I got a huge clue from the box that the domain and range are sets of answers. So if you have forgotten, the set of answers is always written in a brace, and it begins with whatever I'm talking about. So since it asks for domain, I know that those are the x's, and I need to clarify. Is there a limit to the kind of numbers I'm allowed to use? No. So x is an element, that's a squished looking e, of the reals. And the real symbol is this doubled up r, such that is the straight up and down line. And then you list the rule. So this is telling you what kind of numbers you can get, and this is the specific rule. Now I have to stop and think. What am I not allowed to get spitting out? Because that will limit what I'm allowed to plug in. Am I supposed to get imaginary numbers with a square root? No, I'm not. So if I get anything that is less than 0, I'm going to get negatives. So I want this 10 minus x concept inside to be greater than 0. And when I solve that, I will then know what kind of x's I'm limited to. So if I move the 10 over, I have negative x is greater than negative 10. X is, and I'm going to change the signs and make this a 10. However, there was that rule which said if I multiply or divide by a negative, I change the symbol as well. So the numbers that I should have also had here or equal to, it can equal 0. So that should have been carrying with me. So this is the clarifying statement half. X is less than or equal to 10. That's the domain for this function. Example 5 gives us, oh, here's a different one, g of x equals 1 over x minus 2. And it asks to find the domain of G. So I know it's going to be within a brace. Domain is x's. X's are an element of the reals. It'll pretty much be that every time unless there is something specific, which I'll point out to you if we ever see it. And then I know that I am not supposed to have a 0 in the denominator, but I can have positives and I can have negatives. So the only thing I want to limit is that I will not equal this to 0. So x should not be 2. I can plug in every possibility except x is 2. That was example 5. Example 6. Find the domain and range of this function. Y equals the square root of x. Now they called it a function, but they went back to the notation of y equals. They're interchangeable, although typically when we want to use the word function, we will use the f of x or h of x or something along that line. But this, switch back. Find the domain and range for this and graph the function. So I know that for my domain, it will be x is an element of the reals such that, and whatever my rule is. My range will be y is an element of the reals such that, and then I'll have my rule here. So what am I not allowed to plug or to get out, which will limit what I should plug in? I should not have negatives. So x must be greater than or equal to 0. There's nothing to solve there, so I can just go ahead and fill that rule in. So if that's true, what kind of answers are being spit out? Y will be greater than or equal to 0 because it has to only spit out positive answers, and that's how I'm going to state that they're positive answers. Now we have gotten the domain and range. They want us to graph it. So I'm going to just create an XY chart to help me organize which numbers am I plugging in. Now I know I should not be choosing anything that's negative because I need to only choose things greater than 0. So no negative choices. But I can choose 0, that's an easy one. And if I stick to small numbers, I'm usually better off. So and we need at least 3 points. So let's do 0, 1, and 2. So when I plug in 0, what is the square root of 0? 0. When I plug in 1, what is the square root of 1? 1. Ooh, this is a bad choice because 2 is square root of 2, and that's some sort of decimal. So let's change this to a 4. What is the square root of 4? 2. Now I have 3 dots that I can graph. So x, 0, y, 0 is at origin. 1 over, 1 up, 4 over, 2 up, and it's graphing a curve. Now I do know, as a helpful hint, that anytime I'm graphing a square root, I should be getting a curve, so that helps me know where I'm headed. Example 7, find the domain and range of the given function and also graph it. So they give us y equals square root of x plus 4. All right, we know we're going to have our 2 sets. X is an element of the reals such that y is an element of the reals such that. Now, what can I not get out? Negatives. So my x plus 4 must be greater than or equal to 0. Solving, x is greater than or equal to negative 4. And then what kind of answers did we already say? We cannot spit out negatives, so this has to be greater than or equal to 0. Just making sure I didn't have any mistakes there. Yes, and graph. So I'm going to do an XY chart. Again, I'm going to follow my limitations of what I can plug in. Things must be greater than or equal to negative 4. So let's do the negative 4, 0, and I'm not sure what my other choice is here. I'll play with another choice in a moment. So negative 4 plus 4 is 0. Square root of 0 is 0. 0 plus 4 is 4. Square root of 4 is 2. Now I'm looking for something else that I know will spit out evenly, which would be like a 9. So if I plug in 5, 5 plus 4 is 9. Square root of 9 is 3. Okay, now let's do our graph. And again, it's in a square root, so it should look like a curve. Negative 4 and 0. 0, 2. These spaces are a little, I'm gonna do it that way because those are a little narrower. I want to try to keep them even. 1, 2, 3, 4, 5 over 3 up, and my curve is now here. So the curve is narrower, tighter, closer to the x-axis than this one was, and it no longer started at 0, 0. The starting place shifted backwards, which matches the number inside. Those are just more helpful clues later on as our graphs get bigger. Last example in this section says, example 8 on page 154, find the domain and the range of radical x over x minus 2. All right, domain and range. X is an element of the reals such that, y is an element of the reals such that, and I realize when I look at this that I've got two problems. One, I have a root, and one, I have a denominator. I know I should not have this denominator equal to 0, so x cannot be 2, will be one part of my rule. But I also have to keep no negatives here, so my x has to be greater than or equal to 0. Is the 2 greater than the 0? Yes. So I am going to need to list both of these because they're both important. I'm going to start with the rule that x has to stay greater than or equal to 0, and being given with a comma, the x cannot be 2. And if this one had, like if this had been a negative 2, it would have already been thrown out by the fact that I needed to keep it greater than 0, so then I wouldn't have needed to list it even though it was a part of this. Okay, what kind of things did we say we had to have spit out? Is there a limit to the numbers that can come out on this particular example? If I'm plugging in and getting positives only, and I don't have a 0, I could have positives or negatives from this denominator, and a positive divided by a positive or negative will mean I can get a positive or negative answer or a 0 answer. So I don't see a limit to things. So I don't need this extra piece. There is no limit here. So my answer is just my range can be any number possible. So y is an element of the reals. This one did not ask to graph. However, the book chose to show you the graph of what that looks like when you've got a doubled up piece. So just so you can see it here, the biggest difference is in this x cannot be 2. So wherever the 2 is, I know I can't touch this. That creates an asymptote line, which we're going to put down as a dash. So then whatever my curve is created by the root is going to get skewed by this line or get closer to this line, whichever direction it's going. And the same thing will happen on this side. So let's do some choices. And I know I can't choose 2, but let's choose 0, 1, and maybe, no, can't do anything negative. It's got to stay positive. So I'm going to do 4. Okay, so 0 plugged in. Square root of 0 is 0. 0 minus 2 is negative 2. 0 divided by anything, 0. Square root of 1, 1. 1 minus 2, negative 1, so that's negative 1. 4 square rooted to 2, and then 4 minus 2 is 2. 2 divided by 2 is 1. So let's see if that's enough to get both sides. If I know that I have 2 sides, I may have to do more than 3 places, because I'm looking for at least 2 or 3 dots per side. But let's see where we're at. 0, 0, 1, negative 1, 4, 1, 2, 3, 4, and give myself some dash lines here. 4 and 1. This one's skewed up. I'm sorry, the X line's a little bit off. Okay, so I have 2 dots here. That's helpful, but I only have 1 dot this side. I am going to have to create another one. So I know that as I get closer and closer to this asymptote, it skews me downward. I can get close to it, but I can't touch it. And this I can't go past this because I'm not allowed to have any negatives. So my graph actually begins here. It looks like it should be extending, but because I'm limited to only choosing things above 0, you don't have a graph the rest of the way. All right, so now I know 3 is going to be problematic because the square root of 3 is the decimal. So I really want to do another choice that's going to give me something even. Let me try 9. Oh, that's far out to graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, but it should give me a second one. So the square root of 9 is 3. 9 minus 2 is 7. Ooh, so it's 3/7. It's a fraction. It's very tight in there so that I know that it's almost at the 0 line. So this tells me that as I'm going this way, the asymptote skews me up, and here I can't get negative answers, so it's going to stop me at the positive section and just go tighter and tighter that direction. And hopefully seeing that graph is helpful even though they didn't actually ask for it. Now, in section C, they go back to our discussion about the function machine and the fact that I said if you have one x going in, it has to give you an answer, and one number can't spit out two different answers. So on the top of page 155, they show you a series of circles. And in this one, they give a 4 and a 2. And they're giving answers and saying that both of those answers spit out a 3. And that is acceptable. 2 can share an answer. That makes a function yes. In this example, they give a 4 and a 2. And they split the 4 into a 3 and a 5. They do give an answer here for a 6, but this 4 cannot spit out two answers. This is not a function. So if it's not a function, we call it a relation. Just another term for you. And then in this example, they give 4, 2, and 1. 4 has given an answer, 2 has given an answer, but 1 does not spit out an answer, not a function. And because it lacked an answer, it's not a relation either. So it's not really anything. And their final one gives 4, 2, and 1, spitting 3, 5, and 6. It is a function because every number going in has an answer coming out. There are no overlaps in weird combinations of splits, shared numbers, answers, and so on. So this we call a 1-to-1 function because every one x value has one y value. All right, that's all of the major terms on page 155. And then at the bottom, they give a box, important information. We use the word function to describe the mapping from one member of an input set, which is called the domain, to exactly one member of the output set, which is called the range. Each member of the domain maps to an image, so that's another term that they use for the y value, image, in the range. Thus, the word function brings to mind these three rules: the members that are acceptable as inputs, and the algebraic rule, if there's a formula that works, that would go into like the function machine, that can be used to find the unique output that is paired with each input. So this kind of thing is happening. A table of ordered pairs of inputs, kind of like I'm doing here, and outputs where each input member is paired with exactly one output and all equal inputs have the same outputs. In other words, you can't have one number splitting to two different answers. You're going to have a function. And the graph of the geometric points whose coordinates are ordered pairs just described. So you can graph these things in a Cartesian plane. So in example 9 on page 156, they say, look at these diagrams and determine if they are functions or not. So in A, both 4 and 3 share an answer. Yes, that's okay. In B, 5 spits out two answers. Not okay, not a function. In C, M does not have an answer, not a function. D tells you that in the first circle, You are picking any number for x. X is an element of reals. You're putting it into an equation, which they wrote on the line as x plus 2. And will that give you the answer, x plus 2? As long as they don't change the formula there, that one's going to work. So A and D are functions. Example 10. Lists it a different way. Now, when you are given these in a coordinate set, so they're giving you the brace of all of these answers, 1, 2, 2, 3, 3, 4, and 4, 5. Basically, rather than trying to draw out pictures, which you can do, I look for each of the x values and see if I have any of them repeating. 1, 2, 3, and 4. Nope, there's no overlap there. So does everybody have an answer? Yes, this one's going to be a function. In B, I'm looking at all of the x's. 1, 2, 1, 4. Uh-oh, I said 1 twice. So in the first one, 1 gave an answer of 2, and in this one, 1 gave an answer of 3. Can 1 spit out a 2 and a 3? No, not a function. B is thrown out. C, checking my x values. 4, 2, 4, 3. Uh-oh, repeated a 4. So in the first one, it gave me 4, 3. In the next one, it gave me 4, 3. Oh, wait, that 3 is the same, so I don't have a problem there. Does it matter that that the 3 also gave a 3? So if you're picturing it here, this 4 gave an answer of 3. This 3 gave an answer of 3, but we said that was still acceptable as a function. So C still works as a function. And finally, I'm going to check D. 1, 4, -1, 3. I had no repeats. Does everybody have a matching answer? Yes, it does. So D is a function. And the final part of this lesson is the test for does a visual, in other words, not just the numbers like we were doing, but is a graph going to be a function or not? And how can I quickly tell? Oh, I have a box here. Vertical line test. This is the main test to use. And it says a graph on the coordinate plane represents the graph of a function provided that every vertical line, vertical this way, that I can send through the picture intersects the graph in at most one point. I cannot intersect it in more than one place. So their first picture they give you is a curve, and no matter where I choose to draw a vertical line, I only touch one time. That's a function. If this is my graph and I do a vertical line test, no matter where I do it, oh dear, I've hit twice here, so this is not a function. It's a relation. Now on page 157, we have another rule, which is the horizontal line test, and it says a function is one-to-one provided that any horizontal line intersects the graph in at most one point. So if I've already thrown something out and it's a relation, not a function, I don't need to worry about testing it. But if it is a function, it's past the vertical line test. If I draw a horizontal line through it, oh, I hit this in two places. It's not one-to-one. So if I have a line, it's going to pass the vertical. Will it pass the horizontal? Yes, everywhere I'm hitting, I'm only touching it one time, no matter where. So this is a one-to-one. A line is one-to-one. Parabola is going to be a function passing the vertical line test. Now it gets a little tricky because this is always going outward just a little tiny bit, but when we graph it, it looks like it's a solid straight line going up, but it isn't. There's always a little bit of a curve there. So when I do the horizontal, I hit two places, so not one-to-one. So you've got a vertical test to prove function or relation. If it is function, the horizontal test will tell you if it's one-to-one. Final example 11 says, determine if each graph represents the graph of a function. If it is a function, state whether it is one-to-one. So in A, can I pass the vertical line test of something like this? Nope, hit it in multiple places. So I don't even need to worry about the one-to-one. Next one is a curve. Will it pass the vertical? Yes. Will it pass the one-to-one? Horizontal, yeah, I'm only hitting it one place. So it is a function and it's one-to-one. The next one shows a dot with a line and an open circle with a line going this direction. So when I try to test vertically, oh no, I hit this line, I'm hitting like every single spot of this line. So it's not a function. I don't need to worry about one-to-one. And it was discontinuous because it had a gap in it if you need that term. And the last one shows line coming to a dot, another dot, and then going this direction. Again, when I go to test my vertical, I have a problem here because this is a line and I'm hitting multiple places. So it is not one-to-one. I'm sorry, it's not a function.